Good morning, I'm Jaron Rothkop, president of ZeroBase Energy, and I'm going to talk a little bit today about how to power shelters more efficiently. So there's been an enormous amount of innovation in improving shelters, making faster to deploy shelters and more energy efficient shelters, and a lot of that has been led by Dr. Jetty and the Rapid Equipping Force, and it's made it out into the shelters that are available today. There's been a lot less work on the power sources and the major loads and cooling of those shelters. And Phil, who spoke earlier, really spoke to what I think is one of the sources of those problems, is the benefits to having less fuel are distributed to various owners. So there's a benefit to DLA in delivering less fuel, but there's also capability benefits to having fewer soldiers running around with fuel cans. And to being able to operate longer. And so the requirement to reduce fuel is very different from the end user requirement to be able to operate longer or have resiliency or have more manpower available for the mission rather than fueling shelters. So what I'm going to talk about today are some technologies that are commercially available that are being used to significantly decrease the fuel consumption of operations around the world. And ZeroBase Energy is a hybrid power system company. Most of what we do has been inside of the DoD and Army initiatives for net zero, where our equipment has been placed in the field to either reduce the fuel consumption of existing generators or replace those generators. But we also do about half of our work in the commercial world. And in the commercial world, there's a very different mandate, which is to reduce my cost. And if you can reduce the cost by reducing fuel, that's fantastic. If you can do it other ways, they want to see those as well. Also, particularly in the off-grid commercial world, there's a much lower tolerance to risk inside of organizations. And so while everyone in the organization who has procurement authority may be empowered to save money, they're also a bit more risk averse, and so they've been more innovative in the ways that they can go about procuring new technologies. So they may pay for them out of operating expense agreements or power purchase agreements or leases. And what this has led to is a very fast innovation cycle out in the commercial off-grid space. So the technologies that I'll talk about today are ones that we're using and that we've encountered in the off-grid world. So we'll start with the current environment for shelter systems as we've experienced it in working with the Department of Defense. We may have a very efficient shelter, but there's a large ECU that's powering it, usually 6 to 10 ton per billet, and there's a large generator, and that generator is typically in the 30 to 60 kilowatt range. And then the fuel consumption numbers you see below for the 30 and 60. So there's a significant fuel requirement in order to keep that shelter operating and heated and cooled. I don't have the numbers for the entire shelter system program on how much of that load is going to fuel ECUs, but where we've encountered them, it's up to 70% and sometimes more of the energy is just to cool the shelters. So where we started working with the Department of Defense was on hybrid power systems. And the concept of a hybrid power system and its application is very similar to the way a hybrid car works. The engine is there only to charge the batteries or to provide power when the load is very high. And the enabling technologies are very good power management systems, and we feel we have good ones, and advanced battery chemistries. One of the limitations of the existing battery chemistries is that they're very heavy. Another is that they don't operate very well in high temperature. So if you're adding in batteries that increase your cooling load, your end result isn't much more efficiency, because any energy that you're saving is energy that's going to cool batteries. And the telecom industry went through about 5 years of iteration of deploying hybrid power systems and realizing their cooling loads had gone up before they realized that they needed to move to better battery chemistries. So where we've encountered shelters and we've been able to put our equipment between the tactical quiet generators and the shelters, we've seen fuel savings up to 70%, but I would say on average it's around 40%. And so we were scratching our heads a little bit, saying, why are the generators so large? We're realizing these 40% and up savings because the generators are oversized for the application to start with. So what if we took a broader look at the problem? What if we could start with a blank slate of how do we reduce fuel overall for a shelter system the same way that we reduce the cost of operating for commercial operators. So we start with hybrid power systems, and those may be trailer-based or they may be man-portable. We've done a whole range of products for Department of Defense customers. And then we look at the primary source of customer of that power, and it's the ECU unit, and particularly the air conditioning loads. A 48-volt DC-based ECUs and cooling systems are commonly used in very, very hot parts of the world, Africa, the Indian subcontinent. And there's been a very rapid innovation cycle in DC ECUs, and this has been driven by the way that the telecom technology was adopted in those parts of the world. So Africa went from having no telephone system whatsoever to having the latest generation of 4G and LTE networks, and they're considerably ahead of the United States in that regard. So in the US, we're still building massive base stations that require 30-ton ECUs to keep them cool, whereas in Africa, they're moving to systems that require no cooling at all, but they started off with a much lower cooling requirement. And so the DC ECUs are able to reduce their power demand by about 50% right off of the bat. And so that's a good portion of where the energy to power shelter is going, is can be dropped by switching to a different ECU technology. So if a majority of our load is no longer AC and it's DC, we can also drop the requirement for a large AC generator. One of the advantages of hybrid power systems, which are battery-based and solid-state electronic-based, is that they can handle much, much higher loads. So while a 30-kilowatt generator may have been put in place to accommodate a constant 15-kilowatt load, that reserve and that demand response can come from the batteries now instead of from the generator's capacity. So the type of generator can change dramatically. Instead of running an AC generator and running it through rectifiers in order to create DC power, we can move directly to 48-volt DC generators. And the system you see there is a hybrid telecom system for Africa that's able to do a 30-kilowatt peak while using a 10-kilowatt generator as a battery charger. So there's efficiencies to be gained in the generator technology itself of using DC permanent magnet generators, but there's additional increase in efficiency in simply not having to convert that power from AC to DC in the first place. So if we have a system where your power generation is DC and your load is DC, what other technologies can be deployed? Photovoltaics are a DC power generation source. And particularly where you have hard shelters, you have a nice flat roof in which solar panels could be added to the shelter system. One of the key innovations in solar modules for the military has been glass-free solar modules, which is something that we brought initially to DoD in 2009, and they're now becoming the standard when used for expeditionary power. What we've done is work to combine the glass-free solar modules with a technology called PVT, or photovoltaic thermal. These are panels that also move water. And in the interest of saving money in the commercial world, we've moved away from electric-based water heaters to solar heating. And so solar heating and solar power generation can be combined into a single unit. It's a little bit thicker than a conventional solar panel, but not much. And this also has an increase in efficiency of the solar panels. And most people don't know solar panels love the sun, but they don't like heat. They prefer to work in cooler temperatures. So the glycol transfer system that's in the back of these PVT modules moves heat away from the solar modules, making them more efficient, and moves it to where it can be used for showers or for cooking. So when we look at the overall impact of adopting these technologies, we replace a 30 or 60 kilowatt generator and a large 6-ton ECU with a very small generator, a battery-based hybrid power system, some additional power generation resources, which could be solar, they could be wind, and in the case of PVT, they could also reduce some of the energy demand, and DC-based ECUs. Based on what we've experienced, we believe we could realize up to a 70% savings in fuel while creating some added benefits that are tangent to saving fuel. One of them is the weight and space claim goes down considerably. And with the weight and space claim dropping, we can also make all of these systems man-portable. And we've seen quite a few shelter concepts recently that have focused on very expeditionary systems that can go into environments where there's no lift requirement. So we have shelters that can be put together very quickly with 3 or 4 people. But the power assets and the ECU assets are still well above that in weight. And the combination of these technologies would enable us to make lightweight and mobile shelter systems and pair them up with lightweight and mobile power systems that all could be moved into the field very quickly. And the reason I believe these technologies are ready to be adopted is because we're seeing them work in the commercial space. They're not in the lab. They're being proven in extreme environments, and we can help to move them through the DoD evaluation cycle to the point where requirements can be written about them. Thank you. Any questions?
Morning. I have a couple of questions. You talked about on the advanced battery chemistries. Can you give me more details on what those may be? Are we talking lithium?
We're principally using lithium ferrous phosphate chemistries for expeditionary power systems. And we've tried quite a few others, but that is the most stable and the most reliable, and what we've seen is the best trade-off in energy density and weight and safety. For larger installations, we have other chemistries for facilities or for off-grid systems.
Gotcha. The second question was on the 48-volt DC generator. That's primarily generating power for the ECU, is that correct?
Yes.
Okay.
It's essentially functioning as a battery charger, the battery being the primary source and the 48-volt generator being the secondary power source.
Thank you. I want to talk to you after this, too.
Thank you. All right. Thanks, everyone.